after hearing some of the other talks, I thought I might motivate the thing about ASAP. It's kind of a technical talk, so I thought I'd better preface it with some introductory remarks. This diagram is a figure I took out of an experimental book, and it's talking about the process of a growing interface. And what this slide illustrates is there are many processes going on in typical surface growth. And so to model something that takes into all these considerations is pretty hard. And so what one wants is a simpler model, a simpler system. And here's a simple model. You could imagine blocks raining down independently of each other. Oh, I should say, to go back, what we're interested in is the height of this interface. And of course, you could have overhangs and then the height function's not even defined. But let's suppose there are no overhangs. So we're interested in the height, and that height function will be a random function. And that's what we're interested in understanding. So here's a simple model. It's too simple. But imagine blocks raining down independently of each other. In other words, this one coming down and these columns are independent. So if you measured the height of this column, you're just adding together a sequence of independent random variables. And of course, we all know that the height, h, would go like some velocity times t plus some normalization t to the 1/2 times chi. And this chi would be our normal law. And the characteristic 1/2. But of course, this is too simple. Tom, in the earlier lecture, described some of this. There's a KPZ phenomenology, and we restrict ourselves to stochastic growth normal to the surface. And this is what Kadar, Parisi, Zhang, henceforth KPZ, looked at in 1986. And they said the basic object, as I just said, is a random height function, h of x and t. And they argued that this height function satisfies a stochastic PDE, where this is the diffusion constant. This in higher dimensions would be the Laplacian, a coupling constant, and this would be the gradient squared, and then some white noise. And they argued heuristically, based on renormalization group arguments, that instead of this formula, you would have a 3 there. So the fluctuations are on the order of t to the 1/3 rather than square root of t. They made no prediction for this. So there was no prediction. And as Tom said, this PDE is, as written, and needs some explanation, because you're taking something that looks like Brownian motion locally, taking its derivative and squaring it, and that presents problems. I'm not capable of explaining Harier's Field's metal work, which makes sense of this equation. But this didn't stop physicists working on this problem from 1986 on. They looked at various discrete versions, which were finite, and then you wanted to see what you could, from those discrete models, you made certain predictions. And it got to the point where if you had a discrete model and you saw fluctuations on t to the 1/3, you said, I'm in the KPZ universality class. So any model which gave t to the 1/3 was decided to be KPZ universality, even though at this point the KPZ equation wasn't shown to be in the KPZ universality class. So that's so what I want to show first is the experimental work of Takeuchi and Sano. There was work before this. Of course, once the KPZ equation was produced, the experimentalists wanted to see if they could measure something in the laboratory. The problem is, and that's what I hinted at the beginning, this equation was derived for normal growth, and a lot of physical processes included a lot of other processes, and so it was hard to find a clean system that would be in this, you would expect to be normal growth. There would be other processes. Tom showed one of them. A Finnish group took paper and they burned it, slow combustion, and they measured that flame front. And it's generally agreed that this was a difficult experiment. It's generally agreed that they could see the 1/3 but nothing more. They sort of claimed more, but I think it's generally agreed upon now that the data is it's so hard to get good data on this. And you have to do this repeatedly. You have to burn paper after that. It's agreed that there's a 1/3 exponent, pretty much. But it's a very rough experiment. It says nothing about the distribution of this. And of course, we want the distribution not for short time, but for large time. In other words, after it settles, we look at what is this, for large time, what does this distribution look like? So now, here's their experiment. They found a certain liquid crystal, a turbulent liquid crystal, which when hit with a laser would go into a different state. And that different state would then create a wave which they could then look at. So this first experiment, you hit a laser at a point. And now this is their actual data that you're looking at. It's been speeded up by a factor of 5. So the experiment there's the growing surface. And you see it's a little rough on the edges. And what we're interested in is the statistics of that roughness. They did another experiment. Instead of starting with a dot, they let the laser be a line. The first one's called droplet initial conditions, and this one's called flat. And so now they do flat. And again, we're interested in that height function for a large time. When I first, I like to tell this story on myself. When I first saw this years ago, this is done in 2010, Takeuchi was giving a talk on it. And of course, I had the mathematicians point that the laser beam always looks like that. How in the world do you get it to be a line? And he looked at me like I was crazy. He said, well, you use a lens. So that's how he got the line. Okay, so here's a summary, a beginning summary. In the first case, the height function, we're going to say fix x and look at this function as a function of t. Of course, we have to do this experiment 1,000 times or so, to collect the data. And of course, in this, on the flat initial conditions, the height function is just what you expect it to be. So they want to collect data on this h of x and t. Now, on the basis of a lot of computations with discrete models, in particular the work of Prof and Herbert Spohn, they predicted that there were two distribution functions that should describe the long time behavior. These distribution functions are described in terms of a Panlevée-2 equation. Here it is. And we're looking at a specific solution that's called the Hastings-McLeod solution. And so there's some expression for these distribution functions. They arose initially in random matrix theory as the distribution of largest eigenvalues. The F2 was the Gaussian unitary ensemble, and F1 was a Gaussian orthogonal. Subsequently, these were shown to just by there are many universality theorems. Alexander Itz pioneered them with the Riemann-Hilbert method, and Percy Dieph. And they showed that for a large class of, remember in the random matrix theory, we replace e to the minus, we have a potential v of x, and the Gaussian case corresponds to x squared. And for a large class of models, v's, this was shown when you look at the scaling limit, you get the same limiting behavior. So that was an indication that though these were derived, in the Gaussian case, they had a much wider applicability. There was a very important work of Soshnikov. Soshnikov looked at random matrices. He took a random matrix Aij and say, imagine it's symmetric or Hermitian in either case. And he assumed the matrix elements, the independent matrix elements, were IID random variables. In that case, that's called a Wigner matrix. And in that case, there's no Fredholm determinant. There's no formula for the distribution of the eigenvalues. So in some sense, the Wigner matrices are outside the class of integrable models because there's no Riemann-Hilbert, there's no integral equation. But what Soshnikov proved in about the year 2000 was that the distribution of the largest eigenvalue of these Wigner matrices, also in case it was symmetric, the distribution followed F1, and if it was Hermitian, it followed F2. That was really the first indication that maybe these distribution functions apply to things outside the integrable class. Unlike a lot of integrable models in classical mechanics, when you move away from the integral case, you get something completely different. But what seems to be happening in these random matrix models and now these growth processes, you have a domain of attraction. And the current problems are to really understand that domain of attraction. Okay. So the conjecture was based on looking at discrete models, that the droplet case, in the large time limit, this distribution should be F2, and in the flat initial condition case, it should be F1. And that's what Takeuchi set out to measure, well, among other things. So there's the densities. There's not much to say about them in the picture. It's hard to tell, but they're asymmetric. You can, if you want to remember one number, for F2, that's droplet, remember 0.09, and you'll see that number again. And of course, there's no parameters in it, so these numbers are what they are. There's no adjustable parameters in that. Okay, so now I have to unpack this slide. As those who've looked at experimental papers know that a lot of information gets put on one page in data. So to understand the tails better, instead of looking at the density, they look at the logarithm of the density. So that's why these curves look different. Now, so the dotted lines are the data, and that dashed line is, in the case of the droplet, is the F2. Now that doesn't look so good. I mean, you can see. However, what he pointed out was if you look at the first moment slowly decays. The other moments quickly decay to the values that you expect them to be from the F2. If all the moments except the first moment are what they're supposed to be, and the first moment shifted, then a rigid shift of that curve is the effect of changing the first moment. So you can imagine this first, if you go for much, much longer times, you can imagine this first moment, this is the difference. You can imagine this thing settling down to 0. So if you shift this curve, because that would be the case when you're really long time, they show that the data and the experiment agreed about 5 decimal places, which is an incredible accuracy for an experiment on a distribution function. I don't know any experiment that has that precision. And likewise, they said the same thing happened in GOE. And you see the long time, here's the GOE kurtosis, that's at it's a normalized 4th moment, and it's settling down to 0.09, or GUE rather, right here. Okay. You know, I did know the number, but it's less than 1,000, I think. Might be 100. I used to know that number right now. But you have to be impressed by this experiment because, first of all, the experimentalists knew what system to use. I mean, coming up with this particular liquid crystal so that the growth would be normal to the surface. That was problem number 1, and they solved that. And then there's careful measurements. In fact, one theorist, Herbert Spohn, was so impressed with this experiment, he went over to the laboratory in Tokyo to see the experiment for himself. So it's very impressive. Okay, so that's my introduction. It won't be like, well, I'll tell that story later. So now what we're really interested in over the long term is seeing, we want a discrete model which will lead us to the KPZ equation. And it's been known that if you take ASAP, and I'll define that, this is a certain discrete model, that if you look at it in a certain scaling limit, you get the crossover scaling function for KPZ. And that's what Tom mentioned briefly, that if you can calculate a certain distribution function in ASAP, and then you do what's called the weak scaling, which is what Amir, Korn, Quastel did, then you can get the KPZ crossover scaling function. But first they needed the distribution function from KPZ, and that was known by the work of Harold and me. That's the distribution. And what I'd like to describe is the discrete model, which then subsequently led to the KPZ equation. So this work, the first part of the work, is about 10 years old, and we've done some generalizations to blocks, and I will so as I said, that was the introduction. So this is the beginning of the talk. I was at a talk many years ago by Feigenbaum, and I'd given the talk the day before, and it was the talk is scheduled at 10 a.m. to 11 a.m. And so I quit exactly at 11 a.m. And the next day, Mitch Feigenbaum gave a talk, and he started at 10 o'clock. And noon came, and he said, well, that's the introduction. So he had already been an hour over. Now, what he didn't know, or if he did know, he didn't care about it, was this was at Schlumberger. And Schlumberger cafeteria was only open from 12 to 1. So if you're going to have lunch, you're going to have it 12 to 1. And so my colleague David Wilkinson, who was the moderator, said, well, maybe a few more words, you know. So Mitch goes on, and it's about 5 minutes to 1. And you could tell who was employed by Schlumberger because they were all nervous. They're all wanting lunch. And so Mitch is still going on. And at 5 to 1, one stands up, and he claps his hand. He said, that was a great talk, Mitch. And the audience jumped up and rushed to the so I won't go on through lunch hour. Okay. So probably one of the most basic stochastic processes in probability theory is simple random walk. Now you can make time continuous by giving a particle a random alarm clock. That means an exponential distribution with mean 1. So when that alarm clock rings, the particle jumps with probability p to the right and probability q to the left. And that's easy to, you can see this problem in Feller, for example. Now we want many particles, and to be interesting, these particles must interact. So if you just put down the particles and they don't know each other, presence, then you're just looking at the same problem over and over again. So what is the asymmetric simple exclusion process? Well, it's a continuous time Markov process. Eventually, we're going to want infinitely many particles, but we'll start with a finite to start with. And suppose this guy's alarm clock rings. The alarm clocks are independent of each other. And this alarm clock rings. Well, with probability p, it'll jump to the right. Probability q will jump to the left, just like in regular random walk. But suppose this alarm clock rings. Well, and he flips a coin and it comes up heads. There's a particle there. That jump is suppressed. It doesn't get, the clock gets reset and the process goes on. Now, the advantage of using continuous time, you don't have to worry about two of these happening at the same time. That has a measure of 0. So, for example, if this guy's alarm clock rings, he's blocked on both sides, so he doesn't jump. And so all these particles are carrying out these rules, and it's easy to simulate this. Simple refers to the fact that jumps are only allowed one step either to the right or the left. And asymmetric refers to the case that p is not equal to q. That means there's going to be a drift in the problem. So when p equals q, that's the symmetric case. And just to say something about the end, we analyze this problem for fixed p and q. So we fixed the drift and analyzed it. To get kpz, you have to scale p to q to the same 1/2, the symmetric case. So you need the crossover scaling function. Okay, now for one particle, so what are we interested in a stochastic process, Markov process? So typically, the basic object is a transition probability. Suppose I start in state y, and I want the probability at time t that I'm in state x. Now, for a finite number of particles, the state is specified by saying where the particles are. So I can think of x here as a list of where the particles are, and I want the probability starting in state y that I'm in state x at time t. There's a lot of information in the transition probability, and generally these things are pretty hard to compute. Let me explain. This is very elementary, but I'd like to, it gives you some feeling for where these formulas come from. Let's do, I'm going to do something really elementary. I'm going to derive this. This is an undergraduate exercise. But I'm going to derive why this is a transition probability. Well, it satisfies, the transition probability satisfies the differential equation, the Kolmogorov-Ford equation or backward equation. And the way to, so for n equals 1, the state is specified by an integer x. Tells me. And the way to quick way to calculate the differential equation is you write down all the ways to get into the state x minus all the ways to get out of the state x. So if we're at x minus 1, the rate I go into that is from x minus 1 into x. So there's that term. There's a term, I'm at x plus 1 t. And then to get out of the state, so see, here's the particle. I could come in this way. I could come in this way. I could go out this way. I could go out this way. So going out, there's p, and there's a q, and p plus q is 1. So we have p of x. Now this holds for all x in the integers. And what do we want? What's our initial condition? Well, at time 0, what's the probability in being state x given that you're in starting state y? Well, that's the Kronecker delta. So we want to solve this ordinary differential equation. Well, you notice it's constant coefficients, and the standard way to do it would be to use a Fourier series. It's easy to see that the system is separable, and this is a solution. Epsilon of c equals p over c plus qc minus 1. So this is a solution, but it doesn't satisfy the initial conditions. So I can always put an amplitude here. I just fix some complex number in this. That's a solution, but of course it doesn't satisfy the initial conditions. So I'm going to choose this amplitude in a special way, c to the minus y minus 1. And now it's linear, so I can add things together. So I'll integrate it. And I forget the 2 pi i's when I write all this down, or think of it as a measure. And if I choose a contour that includes the origin, then when t equals 0, by the residue theorem, this is the Kronecker delta. And so that's the solution for n equals 1. Now, what about n equals 2? Well, let me give the theorem, and then I'll explain in the simplest case. The transition probability in general, so for n particles, what does it look like? Well, there's an amplitude, a sigma. Well, there's a permutation. So this is going to be a sum over the permutation group. So there are going to be n factorial terms. There's going to be an n-dimensional integral. There's going to be an amplitude. And then you see this term right here looks just like the term in the n equals 1 case, except there's a permutation on the thing. Now, where does this formula come from? It comes from something called beta ansatz. Beta ansatz is well known in the physics literature, but it hasn't been really advertised much in the mathematics literature. One of the reasons is that the way it's usually applied in physics, there's some non-rigorous steps associated with beta equations. We avoid that. Now, what do we have to prove? I'll show you why this is a solution in just a minute. The trick is to show, or the difficulty is to show that when t is 0, this satisfies the Kronecker delta. So when t equals 0, this has to be the Kronecker delta on x and y. And if you look at this a sigma, when sigma is the identity, this guy is 1. And so when this is 1 at t equals 0, by the residue theorem, the identity permutation at t equals 0 gives you the Kronecker delta. So you have n factorial minus 1 other terms. And you have to show they add up to 0. That's where some complex analysis comes in. It's a little tricky. It's tricky enough that when we wrote the paper, we made a mistake. We had to write it in random. But let me explain where this comes from, just the idea. Because if you haven't seen the beta ansatz idea, it's a very clever idea. Beta himself wrote one paper on the subject in 1931. He went on to do other things that won the Nobel Prize. But if you do a Google search on beta ansatz, you'll get about, I don't know, 7,000 hits or something. So it's a popular idea. So let's do n equals 2. So we have 2 particles. So now there are 2 configurations. So here's our lattice. I suppose we have a particle here. We have a particle here. And then there's a configuration where the 2 particles are next to each other. These are the 2 generic cases. Now, if you write down, I won't write it out, but if you write down the differential equation for this, this looks like n equals 1 taken 2 times, because you ask, how can this x1, x2 change with time, well, here's x1, here's x2. You can come in from this side, you can come in from this side, come in from this side, come in from this side, you can go out, you can go out. That's just n equals 1 taken 2 times. So that solution is just n equals 1 2 times. However, if you write down the differential equation for this, there's some terms missing in the previous equation because this jump is suppressed and this jump is suppressed, and so there are jumps that are suppressed. So the differential equation that you write down to here looks different than this one. Another way of saying that is that it's no longer constant coefficient. So what was beta's first idea? Well, see, this holds in the region x1 less than x2 plus 1. And this holds in the region x2 equals x1 plus 1. So you write down this differential equation and you subtract it from this differential. Oh, let me see. So let me think of this as the easy equation, and this is the hard equation. And of course, we all like the easy equation. Now, if this held, see, this holds in this region. If this differential equation held in all of Z2, we could use Fourier series again to solve the problem, because for the same reason we solved it in n equals 1. So what we're going to do is we're going to say, let's look at the solution of this. Imagine this holds in all Z2. Of course, to get this equation satisfied, you take this equation and you subtract it from this equation. And when you do that, you get a boundary condition. And so you replace this hard equation with a boundary condition on this equation, which is just the difference between the two differential equations. So if you can solve this equation, satisfy the boundary condition, then you've solved the differential equation in the physical region that you want. And when you do that, apply that boundary condition. When you apply that boundary condition, it determines this amplitude A sigma. Now, before you rush out and try this on your favorite differential equation, what makes beta ansatz special is if you go to n equals 3 or higher, for n equals 3, there's a new boundary condition that comes from that configuration. This leads to a different boundary condition. However, the magic of beta ansatz is the boundary condition you get from here implies this boundary condition. And if you take your typical growth model or interacting particle system, that's where beta ansatz fails. You can do the 2-particle problem, but you can't do the 3-particle. That's related to something called the Yang-Baxter equation, but I won't go into that. So if you do that and follow beta, and then you integrate. Now, what do we have to show? We have to show that the initial condition is satisfied. And so the choice of this contour, you have to choose the contour so small that all the poles of A sigma lie outside of CR. If you do that, all those n factorial minus 1 other terms cancel when t is 0. In fact, it's a little more complicated than that. If you look at this when t equals 0, and you look at those integrals, they're not 0. But I just said they have to be 0. Well, they have to be 0 in the physical region. So in the physical region, they're 0, but outside the physical region, they're not 0. So, in fact, the thing isn't a probability outside the physical region. So this gives us the transition probability for a set of n particles. Now, there's a lot of information in this transition probability. The difficulty is how do you get it out? Because you got n factorial terms, and ultimately you want to let n go to infinity. So it doesn't look too hopeful at this point. So to extract some information from this, we're going to look at some marginal distributions. For example, we might ask, what's the probability that the mth particle from the left, so now we imagine we have m particles. So we're in a situation where we got a bunch of particles, and here's xm. And at time t, we ask, what's the probability that the mth particle from the left is in state x? That would be a typical question you would. Actually, it's this distribution function. If you can get your hands on this distribution function, and you can scale it in that weak scaling limit, which is what Amir, Koren, Quastel, and Sasimoto and Spohn did, this will give you the KPZ crossover scaling function. But you've got to get your hands on this marginal distribution. Okay, now, how do we do that? Well, let's give an example. Let's suppose m is 2. Here's x1, here's x2, here's x3, and so on. Here's xn. Now we want x2 to equal x. x1 I'm going to write as x minus v1. Or say, did I call it v1 or v? Yeah, okay, x1 minus v1. And I'll call x3 x plus v2, and so on. What do I have to do? Well, to get the probability that x2 of t equals x, I have to sum over all states which lead to this event. Well, in this notation, the v1, this x1 could be, v1 could be 1, 2, 3, x2 could be 1, the v2 could be 1, 2, 3, and so on. And so I need to sum over all these elementary events to get the event that xm of t equals x. Now, if you go back to the formula here, these are all small contours. So when you sum v2, v3, and so on over all integers, you're summing over these c's which have absolute value less than 1, so you can use the geometric series and do that sum. This sum is problematic at this stage because you're summing over a small the contour is small, but it's the wrong absolute value for summing the geometric series. Now the blocks, which I will probably say very little about in this lecture, which is the title. In recent work in the last couple of years, we looked at the probability, say, xm of t is at x, and it's followed by a block. It's a block of length 4. So we calculated these sort of block probabilities. The reason we got interested in these block probabilities is we're interested in higher correlation functions, and these are some of the simplest higher correlation functions. So we're hoping to learn something by doing this. Now, it turns out there's some miraculous identities in this problem. When you do that sum, the simplest case is m equals 1. So x1 of t equals x, x2 equals x plus v1, and so on. So if you do that geometric series and you look at you remember you have the sum over the permutation group. At that sum over the permutation group, you have to, this is the part that depended on the permutations. The u is, just to back up, the u is this function which appears all the time. And in the case of blocks, in the case of when m is 1, it starts at L plus 1. So you have to, when you do that marginal distribution, you get this sum. Well, that sum looks like this, where this is a certain symmetric polynomial. For the simplest case, when the block is length 1, f1 of c is very simple. It's 1 minus the product of the CIs. Oh, I have it written down there. When L is 2, L is 3, the polynomials get more complicated. But the first thing is you have to prove this identity. Well, of course, we first conjectured it. This is when L is 1, by looking at small examples. And then, how many know Doran-Zylberger? No, Doran-Zylberger. He's a famous combinatorialist at Rutgers. And he has on his website, he has a T-shirt. And he has a he's an expert on combinatorial identities. On his T-shirt, he has a complicated binomial identity. And then it says, who do you call? Well, you call Zoran. You call Zylberger, because he's an expert. So we called him, and we asked him, have you ever seen anything quite like this? This is the case L equals 1. And he said, no, but there was a similar sounding problem, not the same problem, in Poglia and Sego. And so he referred us to the problem in Poglia and Sego. And my colleague, after reading Poglia and Sego, I think in about a half hour had a proof. So it pays to call Zylberger if you got it. And now, in general, these polynomials are very complicated to write out. I didn't even write out the L equals 2. But we found a nice representation for them in terms of a contour integral. It took us a while to find this, but if you take this object and integrate it in a certain way, you get these polynomials. They're symmetric polynomials. Now, what happens in this case when you want x2 to be x? So this guy gets summed in this direction. And we're getting summed in that direction means you can't bring the sum inside the integral sign because the contours are for small contours and you're summing the exponents negative. So what do? Here's some complex analysis. You expand the contours out. You do the sum, but of course you want all the contours to be the same, so you bring the contours back in. When you do that, you encounter a lot of poles. You have to calculate the residues at all those poles, and you find you need an identity. And this is a remarkable identity. It has the flavor of an eigenvalue problem. These polynomials, okay, by CS, I mean the variable ck with k not in S. S is a subset of 1 to n. This is the, you normally call this the Q binomial coefficient, but since Q is already used, we'll call it the tau binomial coefficient. And this says if you take this function u and you take the product of all the points in S and all the j not in S, multiplied by FL evaluated at this thing, it reproduces itself like that. Now, what do these identities buy you? Well, they allow you to get an infinite series. Well, this is a finite series. Right. They allow you to get a finite series of this probability. This is the block probability. And this is the integrand. And there's the integrand right there. Now, it turns out the proof for general L proceeds exactly as the same for L equal 1, given the general L identities and the fact that these are polynomials. So there were no new poles introduced. And as is the case for L equal 1, there's a formula for PL, but with large contours. So once you have all these small contours, then you expand them all to infinity. Again, you've got to worry about a lot of poles as you cross. And when you expand them to infinity, you get another formula. It's, again, this sort of same integrand. And remarkably, in this formula, you can let n tend to infinity. So you let n tend to infinity, and you've now got an infinite series expansion for this block probability. But of course, we're interested in asymptotics, and at this point, it doesn't look too good. So now we specify, we specialized to what's called step initial condition. This is the one that leads to the droplet case. So the initial condition looks like that. And we're interested in this. So one starts with this large contour representation and sums over all S with S equal to a fixed K. And lo and behold, there's a kernel that starts appearing. So we have this kernel. There are these extra factors that U. Here's the kernel. And that sum reduces to, well, this comes from the, remember we had a representation for the polynomials. That's due to the polynomials. We get one single integral of a Fredholm determinant because we recognize the term as the Fredholm expansion. And if you go back to L equals 1 case, evaluating the Z1 integral, the block probability, or the distribution function for the nth particle, is reduced to a one-dimensional integral whose integrand is a Fredholm determinant. So we've gone from this n factorial terms, letting n tend to infinity, to a one-dimensional integral that involves a Fredholm determinant. Now, at this point, you might think you're ready for asymptotic analysis, because when you see a Fredholm determinant, the random matrix community knows generally what to do. But it turns out that this one doesn't fit into that terminology. So when we got to this point, I won't read this out, it's a little involved. When we got to this point, my colleague, it always pays to work with a brilliant person. My colleague Harold Whittam said, we need to do a deformation of this operator K such that the Fredholm determinant stays fixed. And he pulls out these lemmas, and I said, where in the world did you get? He said, oh, I did this in the 1960s. So we deform the operator K such that the Fredholm determinant stays the same. And there are these propositions which you can read. It's a little hard to explain it on the board in a short time. And when you do that, you get a new kernel, the so-called J kernel. And this J kernel has a familiar form if you are a random matrix aficionado. See this over this? That's a hint that a saddle point's going to be a good thing. So, in the case of the block, it goes through again like this. So now we can do asymptotic analysis on this kernel. And here's our result. Well, if you look at the distribution function, when m is 1, the L is 1, you get the F2 result. In general, for general L, you get the derivative of F2, that density. And what this is telling you, oh, I should say, it's this formula, in the case of L equals 1, this was the starting point of Amir, Korn, and Costel, and the starting point of Sasimoto and Spohn. They took this formula. We analyzed it in the limit m goes to infinity, t goes to infinity, but the asymmetry was fixed. To get the KPZ equation, which we didn't realize that at the time, to get the KPZ equation crossover scaling function, you have to let P and Q scale to 1/2 in a certain order. And the asymptotics is much harder in that case, and that was what those authors were able to carry out. And doing that scaling of this J kernel gives them the crossover scaling function, which was in Tom's lecture. But if you do this, the interpretation of this result, it looks a little technical. The conditional probability that the nth particle from the left is the beginning of an L block is given that is that at x at time t over gamma has the limit sigma to the L minus 1 over 2. Now when you look at that, that looks like a Bernoulli process. And so if you look at the condition of exactly L particles, you get that. So see, the Bernoulli parameter is the square root of sigma. And it works if you look at unoccupied sites. So the parameter is the square root of that sigma as a scaling. Sigma is how m and t scale with each other. So after all that work with the L blocks, the answer in the scaling limit is that if you tell me where the mth particle is, I condition on the mth particle, the next L particles are just a Bernoulli process, the position. You have a Bernoulli process. That's it.
Any questions or comments?
Well, now I know that you are trying to map those results to XXZ models.
Yeah, you have my notes.
So what this block probability would mean from the point of view of correlation functions?
In the XXZ, you would be looking at what's the probability that you have a block of spins, say starting at x of length 4. What's the probability that you see that configuration? And if you look at the gaps, of course, that would be the probability of a hole.
Yes, but the problem is that you have to take.
Yeah, what it turns out, maybe if I have a couple of minutes still, it turns out ASAP is what we've been talking about, is a Markov process, so it has a generator, L. It's a Markov process. That generator is a similarity transformation, not a unitary transformation. A similarity transformation, maybe X is a bad, let's say T, is a similarity transformation of what's called the Heisenberg XXZ model. So there's a quantum spin model. Now it has to be it can't be a unitary transformation because the spectrum of this is Hermitian, and the spectrum of this is their complex eigenvalues. So what that means, and we never wrote this out for anyone, but it was clear if you know the subject, that our probability distribution function, our transition probability, the work for this translates immediately into the wave function or the Green's function for the short time-dependent Schrödinger operator for the Heisenberg Eisen. So that this Green's function gives you the Kronecker delta at t equals 0. But if you start asking yourself questions about the XXZ, which is what Alexander referred to, this quantum spin system, things associated with probabilities, when you go to quantum mechanics, the probabilities aren't this, but they're things like this. And what does that mean technically? Instead of one sum over the permutation group, you have a double sum. And so all this machinery is, instead of one sum over, you have two, and we're trying to see our way through that now. And I was hoping Alexander would help me.
Does this last result, does that depend upon the sort of distribution initially of the particles?
Well, for finite n, in this case, y would be the position of the up spins in a sea of down spins.
Sorry, I meant the last, the limit one you put on it.
Oh, that was for step initial condition, where they're on the half-life. That's the easiest initial condition to do. I think it's 1 over the square root of p times q, something like that. It would be like delta equals 1. I think there's a 4 somewhere I missed when I told you. Because that's going to be the symmetric case. So you can just take our formulas for this transition probability And just once you see the mapping, you can immediately write down the Green's function for n spins up and a sea of down spins. And we've had that result for 12 years, but we haven't been able to do much with it because of the difficulty associated with the double sum over the permutation group. But we're starting to find new identities, so I'm hopeful today. Some days I'm not hopeful.